Hello, we are in the middle of week 10. I was doing web applications testing, and we had broadly categorized web applications testing into three categories. Testing static hypertext websites, which I did as a part of my first lecture, where we also discussed issues of testing web applications. Last class, I taught you about client-side testing of web applications, in particular one technique called bypass testing. What I want to focus on this lecture is server-side testing of web applications. We'll try to derive two specific graph models that correspond to server-side testing, and I'll tell you what those represent as far as testing the web application software that's present on the server that is concerned. After this, we'll move on and do testing of object-oriented applications. So I'll skip past the slides that we have already discussed in the context of testing web applications. When we did dynamic testing, I told you two categories, client-side and server-side. This is what you saw last time, client-side testing, which basically involved bypass testing is the technique that we learned. I'll move on to server-side testing. This is where we had stopped last time. We talked about how to select test cases when we do server-side testing. Just to quickly recap, we are doing system-level testing of web applications. When I do a method-level testing or I do a component-level testing, then whatever we discussed in the traditional ways like graph-based, logic-based, mutation testing, they all can be applied. I'm assuming that all that is done now. I have the full code integrated into the server with the clients available, and I'm doing system level testing, which comes towards the end of testing phase. And I want to focus on system level testing of web applications on the server side. When it comes to that, when we say test values on the server side, what is the big challenge? The idea is to automatically design test cases or test values that are effective in terms of finding faults for what kind of web applications? For dynamic web applications. That's what we are concentrating on. This is just recapping what we discussed. One option is to select random test cases and test. This is useful sometimes, but not specifically effective all the time. The other idea is to take values from session log files. I will not be discussing this technique in detail, but I'll point you to a reference material at the end of this lecture where you can get some more information about how to test based on user session data. And the third option is for the tester to give inputs based on domain knowledge. One technique that we already discussed in this category was bypass testing, which we did on the client side. One more technique that we'll discuss for the server side based on this is what we're going to discuss today, which will involve deriving graph models from the server side. And as I told you, I'll give you pointers to papers where you can know in detail about all these techniques. Before we move on and discuss server-side testing, when we say I want to define test cases to do system-level testing that will pull out errors, what could be errors related to server-side testing of web application? So errors could be handled by the server. They could be detected and handled by the server. They could be detected and not handled by the server in the sense that they cause an error. In addition to that, not only causing an error, it could result in permanent damage to the server in the sense of corrupting the data on the database that is present in the server and so on. So server, when it handles the test case, the error caused by the effective test case, server could produce a valid response. What is a valid response? A valid response is any response that is produced by the server in response to handling an invalid input that is generated by a test case. Server is aware of the fact that the input is invalid, and it responds in one of the following ways. It responds by providing an explicit message saying that there is a problem with this input is not of this format, and it explains the violation. It could respond by providing a generic error message which is not fine-tuned to the kind of violation that happens, or server could just ignore the invalid input. What do we mean by ignoring the invalid input? It recognizes the fact that it's an invalid input, ignores in the sense of doesn't intimate the tester or the client that the input is invalid, ignores it, goes ahead and does its job normally. The second categorization of server responses could result in a fault or a failure. A fault is an internal fault. it may or may not propagate to being visible in the output. A failure propagates to being visible in the output. Both the cases, there is a server error and it is abnormal in nature. And when the failure gets exposed, what happens is that the invalid inputs that are not recognized by the server, the user also gets to know that it's not recognized by the server, because there is a visible exposure of that error from the information that the server provides to the user, or the server may not provide any information to the user. In fact, a very worst situation can happen, which is the invalid input is so bad that the server does not only produce abnormal errors, it results in corruption of data in the server. Like I told you, it could corrupt the data present in the database in the server, which sometimes could cause more damage than intended. So when it comes to server-side white box testing, what are we going to do? If the source code of the server is available, as I told you, to do method level testing, unit level testing, we can use our usual graph models to test the server. But the problem is the system level testing of server, graph models like control flow graphs don't really tell you about the dynamic behavior of the server. They are static models that describe the structure of the code that is written for the server. They don't talk about how the server put together with the client behaves as a system that is put together. So what we want to do is we want to derive and work with two new graph models that talk about the system level behavior from the server side. When we talk about the server-side code, you remember 2 classes ago I presented to you the architecture of web application, which involved several different layers. There was a layer containing data, then there was a layer that contains the user interface. In between these 2 layers, there was a presentation layer. What we are focusing on is the code that is present that corresponds to the server as it is given in the presentation layer. From this code that is present in the presentation layer of architecture of a web application, we are going to derive 2 different graph models. The first graph model that we are going to work with is called Component Interaction Model, abbreviated as CIM. The second graph model that we are going to work with is called Application Transition Graph Model, abbreviated as ATG. I'll first begin with the CIM model, then move on to ATG model. So as I told you, please remember we're looking at the server-side code as it's present in the presentation layer of a web application that is dynamic in nature. So when it's dynamic in nature, a particular website can be created in different ways in response to different requests. And it is created by dynamically generating HTML forms. And when HTML forms are dynamically generated, it's generated in sections or fragments. And there are sections or fragments that are specifically called atomic sections that are very important for us. So what is an atomic section? An atomic section is a section of a HTML file with the following property. If one part of the section is sent to the client, then the entire part of the section is sent. Before moving on, I'll take an example and explain to you what it is. So here is how the code looks like. This thing that I bracketed as different rows in the table corresponds to some server-side code present in the presentation layer. So it first gets a response from the client and then it prints out this chunk. First, remember, it is to print out a HTML file to be rendered in the web browser interface of the client. And every HTML file begins with a HTML tag, followed by a header tag, followed by a body tag. So I have put all these three print statements that print the beginning of the HTML header tag, the HTML main tag, followed by the header tag, which prints the title, and ends the head tag, followed by the beginning of the body tag. All these 3 are printed together, so they are put as one row in the table and constitute one atomic section. After that, if the user is authenticated, if the user is a valid user, then a welcome message is printed and input is being read. If the user is an invalid user, go down here, which is the else part, then nothing is printed and the HTML file is ended and closed. So an atomic section is a chunk of HTML file such that if one part of the file is output to the client, sent for printing by the client at the end, then the entire part is. Here this is one chunk that is printed. This is the next chunk that reads the, if the user is validated, it prints the message. This is the next chunk that is printed. This is the next chunk which is empty. So that's what is described here. An atomic section is a section of the HTML file with the property that if any part of that section of the HTML file is sent to the client, the entire section is. Atomic sections might themselves include scripts written in JavaScript. It could be empty. Atomic sections basically satisfy all or nothing. If the thing is printed, it's printed in its entirety or nothing is printed. One full HTML file could be printed as an atomic section. Atomic sections could be empty. Another related terminology that we will need is the notion of a content variable. What is a content variable? It's a program variable that provides data to an atomic section. So now if you go in this example, these things that I have bifurcated by using these lines to see how the code is fragmented, the ones that are marked in red on this column on the left hand side represent atomic sections. So there are 6 different atomic sections. If you notice, there's one atomic section P5 which is completely empty. In this scenario, why is it empty? It is empty because the user is not been validated. So they don't want to print the welcome message and read the data and print it. So they print nothing, but they close the body and HTML file so that the empty HTML file can be rendered back on the client's web browser. Content variables, as we see, are colored in green. So here title is a content variable. What is a content variable? That generates data dynamically. So title of the web page is dynamically generated. For example, let's say if it's a bank page, it could print welcome message followed by your name as a part of the title, and the name part of the welcome message is dynamically generated. This data, whatever it is which is stored in this vector element, it could be data related to your statement. If it's a bank page, it could be data related to your marks. If it's your marks page, it could be anything. This data that is dynamically generated is also called content. So I hope these two terminologies are clear: atomic section and content variable. Moving on, our 2 graph models that we will be considering will be built on atomic sections and then further on the first level graph model. So component interaction model, CIM, as a graph, what does it do? Models individual components, combines atomic section. It is intra-component, means it talks about interactions within a component. Nodes of a component interaction model graph will be atomic sections. Transitions will tell you how to move from one section to the other. With that thing, it will model one particular component of a web server software that is present in the presentation layer. Building on the CIM model, we will later on define the application transition graph, or the ATG model, where each node of the ATG model will be one CIM graph and edges would be transitions amongst the CIM graph. Because each node is one CIM graph, an application transition graph is a inter-component graph. That is, it models interactions across components. I'll first begin with CIM. So before we understand CIM, we need to know what component expressions are. Atomic sections, which we saw a little while ago, they can be combined to model dynamically generated web pages. How will you combine atomic sections? If you remember, when we did mutation testing, I had introduced you to regular expressions. Regular expressions is one standard way of combining atomic sections. So this sequential operator, this is P1 is one atomic section, P2 is one atomic section. P1 dot P2 means atomic section P1 is followed by atomic section P2 in a sequential way, in this order. This is the same syntax as that of a sequential concatenation in a regular expression. Selection, which corresponded to plus as we defined it in regular expression, is union, which means either print P1 or print P2. Print 1 of P1 or P2. Iteration is again very similar to the regular expression iteration. Print 0 or more occurrences of the atomic section P1. In addition to these 3 standard regular expression like operators, we also have the operator of aggregator. What does aggregator do? The syntax is like this. It says P1 and then you open these flower braces or curly braces and then you print P2. So the way to read it is, for P1 is printed as an atomic section and inside the atomic section P1, P2 is printed. Right? So these are the 4 ways to combine component expressions. If you go back to this example that we saw, atomic section P1 is printed once. This begins the HTML file, and then this is a decision statement which corresponds to the internal code present in the server. If this decision is positive, turns out to be true, which means the user is validated, then atomic section P2 is printed, where P2 begins with a welcome message. Then what does this one do? This one goes through the input, the data containing, the input is present in this array called my vector. So this is a for loop that goes through that, and as it's going through the thing in different paragraph, in a new line break, it prints each element as it's reading from the input, and it keeps doing that, and when it ends, it exits and comes out. So this is printed as many times as there are inputs to be read. So the sequential composition of that thing would be, you print P1 and then you do P2 and then you either print P3 or P4 as many times as the for loop would run, or if the user is not validated, print the empty atomic section P5. Whatever you do, follow it with P6, which closes the HTML body and the main HTML tag. So this is how atomic sections are combined, and this is the graph also corresponding to the component interaction model. Given a particular web server code, there are algorithms to generate these expressions automatically. As I told you, I'll give you references from where you can get these algorithms to do it. So now, what are the various kinds of transitions that can occur in a component interaction model? There are 5 different kinds of transitions. A transition could be the result of a simple HTML link. The anchor tag, which many of you might know, is one such example. In a part of a HTML text, I just use the anchor tag and hyperlink to another page. So this is an example of a static link or a simple link. The next example of a transition could be a form link transition, which is basically you type in some data like your user ID and password, and you are exposed to a form from which you type in this data and you submit. When you submit, you create what is called a form link. The third kind of link could be a component expression transition, which is a particular execution of a particular software component causes one whole expression to be sent to the client, an expression like this, like the one that we saw earlier. The fourth could be an operational transition. What does this mean? This means that it's a sudden transition that comes as an unplanned input from the user. Typically, if you're accessing your bank site or if you're doing your online shopping for some reason and you have typed in your credentials and you're accessing your bank site, you will often find information which says do not press back or refresh button. Why? Because the particular data is being encrypted and sent across from the client, which is the instance of your machine from which you are accessing your bank, to the server. This takes a while for a server to process that data, validate it and print it. And it might, if you run out of patience and press back button, then you interrupt the processing of the server. And those kind of things are called operational transitions. It's a transition that was not as a part of the planned routine that disrupts the operations that the server performs on particular client input data. Typically by pressing back button, forward button, refresh button, or you change the URL, browser reloads from cache. All these things cause abnormal operational transitions. The other thing could be what is called a redirect transition, which is an internal transition done by the server. It is typically not visible to a user who's sitting on the client. To give you an example of what a redirect transition could be like, for example, the server code could be modularized, and for the server to be able to particularly, let's say it has to fetch some kind of data from a database which is sitting in another server, and let's say the main web server has access to the database server. This main web server could do a redirect transition to the database server, get the data or validate the data and accordingly respond. So that kind of transitions are called redirect transitions. So transitions that are simple hyperlinks, transitions that are forms, transitions that correspond to component expressions, transitions that are abnormal, which cause abnormal interruption in server processing of data, and these are transitions that are internal to the server. So how does a CIM model look like? We'll expand on what we did in this model here. I just told you here for my vector element. Let's say this is something that prints the marks of a particular student. A student is waiting for results, let's say of its 10th standard or 12th standard or GATE exam. Results are going to be made available online on a particular date. And if the user is valid, this actually reads the data of the score or the marks corresponding to the subject and prints it out. So what I'll do is I'll retain some parts of it, the later parts of this, but I'll elaborate on this part of it. So this is an example of a grade servlet, grade in the sense of a student grades. So you start by saying you request for ID, request for password. If the password is wrong, then you request for retry, and then you get a response. And then you start printing. This is the header tag, this is the body tag. If the ID and password are correct, then you start printing the grade report. This is the title, and let's say some student might have written 5 courses, 6 courses, 4 courses, different number of courses. So you run a loop through the number of courses, print the course name and the grade. If the password is wrong, then you are allowed 3 attempts to correct your password. So in the retry is the variable that captures the number of attempts. If retry is still less than 3, then you say your password or ID was wrong, and again redo this thing of password, retry, submit, and update retry here. And when the number of attempts cross, then you say I have sent a mail to professor indicating that this is a problem. So is it clear? And then after this P4, I end it with the same P5 and P6 which I have not repeated, which is empty. P6 closes the HTML tag. So let's say this is an example of a code on the server which prints the grades. So now let's generate the component interaction graph model for this. Start page will be login.html, which is not described here. And then atomic sections will be P1, P2, P3, P4, which are these. P5 and P6 generated from the earlier side. And like we did last time, always do P1, which is the header and information, and then do P2, which is validating, and print P3 as long as there is code, or P4, which is retry, P5 retries crossed, end it with P6, which is the final ending of HTML tag. So what are the transitions? From login.html, I go into the grade servlet, which is this component, this entire component, and inside grade servlet, I can do transitions from P4, which talks about sending mail, or it talks about number of retries of a password, and so on. This is that part. Just concentrate only on this where I'm pointing my mouse to. P1 could be followed by P2, any attempts of P3 or P6, or P1 could be followed by P4 followed by P6, which corresponds to password retrials up to 3 times, or P1 could be followed by P5 could be followed by P6, which corresponds to failure after the 3 retrials and empty page is printed. So this is how a CIM looks like. I hope this example explained to you to a certain extent how a CIM model looks like. Now moving on, we will look at how an application transition graph model looks like. If you go back to the slide where I introduced these two models to you, I said an application transition graph is also a graph where each vertex or a node is one CIM graph and edges are transitions amongst the components. So it models inter-component behavior at the presentation layer. Let's say to define an application transition graph, let's say we have a finite set of web components called gamma. Capital theta is the set of transitions amongst the web software components. This could include HTTP request, sending of data, abnormal button presses, any kind of transition that we discussed earlier. And capital sigma is the set of content variables that define the state of a web application, and alpha is the state of start pages. So in the Great Servlet example, there could be 4 different web files. Login.html, whose code I didn't give you. Let's say it's a static website that just has a form. Great Servlet, whose code we saw. Send mail, whose code I didn't give you, but let's say it's similar to the Great Servlet in the sense that it picks up the email ID from the database and sends an email. And then there is another static page, let's say syllabus.html. So the transitions could be from the login page, you could go to a page where you get the syllabus.html, fetch your data, or from the login page, you could directly go to a page where you print the grade details, provided ID, password are valid and retries within the allowed amount. And from the Great Servlet page, you could go to a page where the grade report is sent by email. Or from the Great Servlet page, you can go back to the Great Servlet page because one of the attempts to enter user ID and password failed and you're still retrying within the 3 attempts to get it right. And what is the set of actions? Set of actions or the variables which define are what is the ID, this should be ID, not IS, ID name, password and the number of retries. The beginning page is the login.html page. So here is how the ATG graph looks like. Through a GET request, I go to the first page, which is a login page, and then I can go to the syllabus page where I print it. Somebody might just want to know the syllabus. You print it and you stop. Nothing more to do. From the login page, if I get ID and password, I am allowed 3 retries as long as retry is less than 3. So here is where I print the beginning thing. If my ID and password is wrong, I go back and retry. This is presented loose-ended here, but the internal code of the server will ensure that this transition happens only 3 times. But if everything is correct, then the grade card and the marks are printed here and you exit. The number of retries exceed 3 and the ID and password still don't turn out to be right, then you print the empty page and exit. Whatever it is, you go to the send mail page. So this whole entity describes the complete behavior of the server-side software as it is present in the presentation layer. And inside this ATG, in one of the pages, Great Servlet, in one of the components, Great Servlet, we have actually sort of zoomed in and looked at the CIM model, which I discussed to you. Similarly, you could have another CIM model here inside send mail, because this could also be a dynamically generated server code. But this is probably static because it just prints the syllabus, and this could probably have a form. So if you kind of zoom into each of these nodes, there could be similar internal graphs that correspond to the CIM graphs for each of these modules. So this is how you generate graphs corresponding to system level dynamic behavior of a web software that is present in its presentation layer. Once you generate this graph, you can do whatever you want with it. You can do path testing, you can skip and test, you can generate test cases that correspond to identifying various errors. So testing based on atomic sections, which in turn involves testing using ATGs and CIMs, it provides a nice mechanism to capture fundamental system level behavior of a server software. And please remember, software of the presentation layer, not the database layer. Such a testing through examples has been proven to handle distributed integration of various websites. It can handle dynamically generated web pages to see if all the different ways of generating web pages can be done correctly. It can handle operational transitions, which if you remember, I told you were interrupts because somebody pressed the refresh button while a page was loading. Somebody pressed the back button while a page was loading. You can test for all these features of a server at the system level. The problem is that the graph CIM and ATG partly have to be generated manually. ATG graph, we don't know of an automatic way to generate it by looking at the server-side software, and this can be non-trivial. But once somebody is willing to put in that effort and generate the graph, then it gives valuable information to test for all these properties of a web server. That's the point that is being made. So that summarizes one technique for doing server-side testing of web applications. So just to recap what we did from the beginning, I introduced you to faults in websites, and then we looked at client-side testing, one technique, bypass testing. In this lecture, I told you about graph-based testing for system-level testing of server code of web software. What is left as far as web application testing is concerned? This area is still very rich, lot of open problems. For example, if you consider how does data flow graph model? If you see the ATG graph and CIM graph that we looked at, models only control flow, but at the system level, doesn't really talk about what happens to data flow. There is no clarity on data flow testing for system level web applications. People don't know how to do definition and use across dynamically generated web pages. So that's very much an open problem that is left for working. As I told you, ATG cannot be generated automatically. Algorithms that will look at the server code on the presentation layer and generate ATG automatically would be very valuable. And for example, if there are multiple users, if there's session data, if there's concurrency in the sense of multiple clients from different geographically located places handling, we still don't know how to generate graph models and test. All these are still rich in open problems that people could consider working on. Before I wind up this module on web applications testing, I would like you to point to a nice website which maintains various web testing tools. In fact, if I know it right, it has more than 500 different web testing tools. So I just told you that there are several open problems, and this website has almost 500 tools. So you can imagine the richness of web application testing. What we have done in these 3 lectures is probably to just scratch the surface of web application testing. This is the URL of the website. It's maintained by this gentleman called Rick Hover. One thing to note before you access this website is that the focus of my lectures was on concentrating on system level functional testing of web application. I'm testing the core functionality on the client side, the server side, in terms of does it do what it's supposed to do in terms of meeting its functionality. The kind of testing techniques that I discussed with you doesn't involve things like performance testing, stress testing, load testing, which are non-functional testing. A lot of tools listed in this website talk about non-functional testing of web applications. So in case you're accessing this website, please remember that that's something that we didn't discuss in these 3 lectures on web applications. So to conclude this module on web application testing, the web applications offer many advantages. They use several different technologies, and as I told you, there are still several fascinating open problems to work on. And I believe that it's only the beginning of, if you want to coin a term called software engineering specific to web software engineering, research in it is still at its beginning. What we looked at were 2 techniques, bypass testing and graph models based on atomic section. Bypass testing on the client side, atomic sections on the server side. This is still a very active and rich area. So here are some publications that I pulled out the material from. The first part, which I didn't do, which is testing on the client side and on server side based on user session data, that you can find it in this paper by Elbaum, Rodhamel, Kare and Fisher. It's an IEEE Transactions and Software Engineering paper, about 12 years old. The thing that I taught you, bypass testing of web applications on the client side, appeared in this paper by Ofut, Wu, Du and Huang in ISRI 2004. This paper is another early paper that appeared in ICSI 2004, which talks about graph models of web testing, the kind of things that I told you about, 5 different transitions between CIMs. All those things you can find in this paper by Recca and Tonella. The server-side testing that we discussed, which is modeling the presentation layer as CIM and ATG, that was in the paper by Jeff Ofut and Wu, which appeared in this journal, Software and Systems Modeling, in 2010. Feel free to pick up any of these papers if you want to know additional details, or you could ask me in the forum if you have any specific questions. If I know it, I'll be able to answer it, would be happy to do so. So in the next module, we'll begin object-oriented testing. Thank you.